There is a comet that has drawn the attention of America's most distinguished scientists, and the strange part is that a professor from Harvard is putting forward the theory that it might actually be alien technology. At this very moment, something that seems impossible is moving toward our sun at a speed of 36 miles per second. This visitor is believed to carry ice even older than Earth itself, shaped in the fires of a distant star system billions of years ago. We will witness the moment telescopes capture this cosmic uninvited guest, discover why its speed breaks all known records, and see how a droplet made of ancient dust rewrites our understanding of interstellar space. We are tracking the third confirmed messenger coming from beyond our solar system. This traveler journeyed for longer than life has existed on our planet, and now it stands before us. If you subscribed to our channel and liked our video, now let's move on to the investigation. As the robotic eye scanned the southern sky, it was searching for threats that could end our civilization within minutes. What it found completely changed what we know about visitors from deep space. The asteroid observation system in Chile's Atacama Desert, while hunting dangerous rocks rapidly approaching Earth, detected something that should not have been there. There was a faint point of light moving among the stars. But this mysterious visitor was not behaving like any asteroid or comet ever recorded before. It was moving in the opposite direction. Imagine our solar system as a massive whirlpool with the sun at the center and the planets orbiting in predictable paths. Everything born here follows the same current, like leaves drifting in a stream. But this mysterious visitor was swimming against the current. It was cutting through our cosmic neighborhood at an angle that defied physics. It was not following any orbit that could be bound to the sun's gravity. The Discovery team realized hours after the first detection that they had found something extraordinary. While most space rocks travel at thousands of miles per hour, this object was moving through the void at speeds that seemed impossible. Initial calculations showed that it was moving fast enough to escape not only our solar system, but even the gravity of nearby star systems. The results shocked the astronomical community. If the math was correct, they were looking at only the third confirmed visitor from interstellar space in human history. The first was the cigar-shaped mystery called Oumuamua in 2017. The second was the comet Borisov in 2019. Both had sparked intense debates about their nature and origins. But this new arrival was different in a way that even seasoned astronomers paused. While Oumuamua was roughly the size of a football field and Borisov was about the size of a city block, early estimates suggested that this newcomer overshadowed both previous visitors. We were likely facing an object kilometers long, carrying ice and rock from a star system so distant that the light coming from there takes decades to reach us. The telescope in Chile had accidentally opened a window into deep cosmos. Within 72 hours, observatories on 6 continents turned their instruments toward the same region of the sky. They were eager to capture every photon of light from this cosmic time capsule because they had limited time before it slipped forever into the outer darkness. Yet the most shocking discovery was still hidden within the data, waiting to rewrite our understanding of how fast objects can travel between the stars. Imagine standing beside a highway where cars are moving at lightning speed. When astronomers calculated the true speed of our interstellar visitor, this is exactly what they discovered. This object was not just fast by space standards, it was moving at exactly 36 miles per second every second. To put this into perspective, you could travel from New York to Los Angeles in less than 2 minutes. A journey that takes a commercial airplane 6 hours would be completed before you finished reading this sentence.
This measurement sent shockwaves through the scientific community because it shattered all previous records for interstellar objects. Oumuamua had impressed everyone at 16 miles per second. The comet Borisov had managed 20 miles per second. But this new visitor was moving at nearly twice the speed of anything we had seen coming from beyond our solar system. What made this speed so remarkable was not just the number itself, but what that speed revealed about the object's incredible journey through the galaxy. Like a detective examining bullet trajectories, astronomers can read the stories of cosmic travelers from their speed and direction. The faster an object moves, the more energy is required to accelerate it, and the more violent the event that initially hurled it into interstellar space must have been. This comet had been ejected from its home with such immense force that it reached what scientists call hyperbolic speed.
Imagine throwing a ball so hard that it not only escapes Earth's gravity, but continues moving away from our entire solar system. The energy required is unimaginable, and it becomes clear that our visitor survived a cosmic catastrophe of extraordinary magnitude. Speed also meant that time was running out. Unlike asteroids that orbit our sun for millions of years and give scientists decades to study them, interstellar visitors pass through our neighborhood like cosmic shooting stars. At a speed of 36 miles per second, this object would cross our entire solar system in less than 2 years and would spend only months within the range of our most powerful telescopes. Observatory directors around the world began emergency scheduling sessions. Every clear night was precious. Every hour of telescope time could capture data that might never be available again. An astronomical gold rush was beginning as researchers raced to unravel the secrets of this ancient traveler before it vanished into the emptiness between the stars. But speed was not the only thing that made this visitor special. The mathematics of its orbit concealed an even more astonishing truth. The numbers were telling a story that seemed impossible. When astronomers traced the visitor's path backward through time, they discovered something that left even seasoned space scientists speechless. This object had not merely entered from the edge of our solar system, it had crossed the vast emptiness between star systems, traveling for millions of years through a cosmic desert where nothing should survive. The evidence was hidden in a single mathematical concept called orbital eccentricity. Think of eccentricity as a cosmic identity card that reveals the true nature of an object. Everything born in our solar system has an eccentricity of less than 1, meaning its orbit forms a closed loop around the Sun. But objects coming from interstellar space have eccentricities greater than 1, creating open-ended paths that never return. Our mysterious visitor recorded an eccentricity score of 6.2. That number may sound modest, but in the language of orbital mechanics, it represents something extraordinary. For comparison, Oumuamua recorded 1.2, while Borisov measured 3.6. This newcomer was following the most hyperbolic orbit ever recorded, meaning it was more clearly interstellar than any previous visitor. The mathematics revealed an even more astonishing truth. When scientists reversed the orbital calculations to estimate where this object came from, they discovered that it entered our solar system from the direction of the constellation Sagittarius. This was not a random wander. The visitor had followed a precise trajectory through the galaxy, threading the needle between the gravitational influences of countless stars. But proving an interstellar origin required more than just orbital mathematics. Scientists needed to confirm that it was impossible for our sun's gravity to capture and retain an object moving this fast. The calculations were conclusive.
Even if this visitor passed directly through the sun's corona and absorbed the maximum possible gravitational acceleration, it would still have enough speed to escape our entire solar system. After weeks of verification, the International Astronomical Union made it official. Our visitor received the designation 3I/Atlas, marking it as the third in this special category of cosmic travelers in human history. However, the mathematical proof of its alien origin was only the beginning. The object's physical size would prove even more striking. Standing next to this interstellar giant would be like an ant staring up at a skyscraper. Initial size estimates showed that our cosmic visitor had a diameter between 6 and 12 miles, making it a true giant compared to previous interstellar objects. To grasp the difference in scale, imagine Oumuamua as a football field. This newcomer would be equivalent to an entire city, complete with suburbs stretching beyond the horizon.
Calculating the size required a piece of detective work worthy of Sherlock Holmes. Since we cannot physically measure objects billions of miles away, astronomers had to use light itself as a ruler. By analyzing the amount of sunlight reflected by the visitor and comparing that brightness with its distance from both the sun and the Earth, scientists were able to estimate its surface area and therefore its approximate size. The Hubble Space Telescope provided critical measurements when it captured the sharpest image ever taken of an interstellar object. The image revealed something resembling a cosmic teardrop with a bright central nucleus surrounded by clouds of dust and gas stretching for thousands of miles. This coma, as astronomers call it, extended across thousands of miles, but within that hazy glow was hidden a solid core of ice and rock that had traveled across the galaxy.
What made the size so important was not just its impressive dimensions. Larger objects can survive interstellar journeys that would completely destroy smaller travelers. Think of cosmic radiation like sandblasting that slowly erodes everything exposed to it. Over millions of years in the void between stars, this invisible bombardment can wear down entire mountains of ice and rock. The significant mass of our visitor meant that it emerged largely intact by withstanding this cosmic erosion. The outer layers may have been stripped away during its long journey, but enough material remained to create the spectacular display we are witnessing. Every grain of dust drifting away from the core represented matter that had formed in an alien star system and was now mixing with particles from the realm of our own sun. The size comparison also revealed something about the violent events that originally hurled this object into space. Ejecting something this large from a planetary system requires extraordinary energy. We are talking about gravitational slingshots involving giant planets or stellar explosions powerful enough to fling city-sized chunks of ice across interstellar distances.
But size alone cannot explain why this visitor was so special. The factor of rarity told a far more intriguing story about our cosmic neighborhood. We live in an era where discovering one of these cosmic messengers is like finding a needle in a haystack on a universal scale. Consider the incredible improbability of what we are witnessing. In all of human history, with thousands of years of sky observations, we have confirmed the existence of exactly 3 objects originating from beyond our solar system. That means there have been fewer interstellar visitors than humans who have walked on the moon. Rarity makes each detection a scientific event comparable to discovering a new continent. The numbers tell a story of cosmic loneliness. Our galaxy contains more than 400 billion stars, and many of them host their own planetary systems. Logic suggests that these systems should constantly eject comets and asteroids into interstellar space, creating a steady flow of travelers between the stars. Yet in practice, finding these nomads requires extraordinary luck and timing. Think of interstellar space as a vast, dark ocean where occasional visitors pass through a small section of our cosmic shoreline. Most fly by undetected, either because they are too small, too distant, or pass through regions of the sky that our telescopes are not watching. The fact that we have detected 3 suggests that thousands have passed through our neighborhood unnoticed. Each confirmed detection represents a breakthrough in our observational capabilities. Oumuamua was discovered by the Pan-STARRS telescope in Hawaii, designed specifically to scan wide areas of the sky for moving objects. The comet Borisov was found by amateur astronomer Gennady Borisov using equipment that would have been unattainable just a few decades ago. Our newest visitor was captured by the ATLAS system, a network of telescopes dedicated to protecting Earth from hazardous asteroids.
Rarity also creates urgency. Unlike planets or stars that remain visible for centuries, interstellar visitors offer only brief windows for study. By the time we detect them, they are already moving away from us at speeds that make long-term observation impossible. Scientists may have only months or years to collect data that might not be available again for decades. This scarcity turns every measurement into valuable scientific currency. Every photograph, every spectroscopic analysis, every radar reflection represents irreplaceable information about objects that preserve samples of environments billions of miles from home. The 3 confirmed visitors also represent 3 different categories of cosmic travelers. Oumuamua remained mysterious, likely asteroid-like. Borisov behaved like a typical comet. Our newest arrival was proving to be something entirely different. While Oumuamua was a riddle wrapped in cosmic mystery, this new visitor was writing its autobiography in light. The contrast between our current guest and its famous predecessor could not be more dramatic. Oumuamua frustrated scientists by revealing almost nothing about its true nature. It showed no signs of the gas and dust emissions that characterize normal comets. Its surface was stubbornly inactive, offering very few clues about its composition or origin.
This new arrival was the complete opposite. A cosmic exhibitionist putting on a spectacular show for anyone with a telescope. Just days after the discovery, observers detected clear signs of cometary activity. A hazy atmosphere called a coma had formed around the nucleus, and as the ice sublimated under solar heating, a faint tail began to develop. The difference was like comparing a locked safe to an open book. While Oumuamua kept its secrets hidden beneath a mysterious reddish surface, our new visitor was actively sharing samples of its internal composition with each passing day. Every gas puff and stream of dust particles represented direct evidence of conditions in an alien planetary system. Spectroscopic analysis revealed water vapor, carbon compounds, and organic molecules streaming away from the nucleus. These were not just random chemicals, but complex substances telling stories about the star system this object originated from. The presence of water suggested formation in a region cold enough for ice to permanently condense. The organic compounds pointed to chemical processes similar to those that occurred in the early history of our own solar system.
The behavioral differences were just as striking. Oumuamua had mysteriously accelerated as it passed close to the Sun, sparking speculation about everything from gas outgassing to alien technology. Our current visitor was accelerating exactly the way comets are supposed to, following predictable patterns that matched computer models of ice sublimation and dust emission. Even the timing was better. Oumuamua was discovered when it was already leaving our solar system, giving scientists only weeks to collect data before it vanished beyond detection limits. This new arrival was detected while it was still approaching, providing months of observation opportunities as it brightened and became more active. The difference in communication may have been the most important distinction of all.
Oumuamua whispered its secrets so quietly that many of them will remain unknown forever. This visitor was almost shouting its story across the electromagnetic spectrum. Every molecule streaming away from it carried a message written in the chemical alphabet of an alien world.
Scientists analyzing the object's emissions were like detectives examining evidence from billions of miles away and millions of years in the past. Each type of gas and dust particle revealed specific conditions that existed when this object first formed around a distant star. The chemical fingerprints were literally extraterrestrial, authoring our first detailed look at material shaped in an environment completely different from our own solar system. The spectroscopic data painted a fascinating picture of alien chemistry. Water vapor dominated the emissions, confirming that this visitor formed in a region cold enough for ice to condense permanently. But water was not alone. Scientists also detected carbon monoxide, carbon dioxide, and a variety of organic compounds, suggesting a chemically complex environment during its formation. Think of these molecules as cosmic DNA, with information about their birthplace encoded in their structures. For example, the ratios of different water isotopes can reveal the temperature and pressure conditions under which the ice originally crystallized. The organic compounds provide clues about the types of chemical reactions that occurred in that distant planetary system.
What made these detections extraordinary was their clarity. Unlike studying exoplanets, where we glimpse chemical signatures through filtered starlight, here were direct samples passing right by our telescopes. Every gas molecule and grain of dust represented uncontaminated material from another star system, preserved during a journey of millions of years through the deep freeze conditions of interstellar space. The chemical analysis also revealed something unexpected about the visitor's journey. Cosmic radiation should have gradually altered the surface composition during its long passage between the stars, yet the emissions suggested relatively pristine conditions beneath the outer shell. This indicated that the object was large enough to shield its interior from the harsh environment of interstellar space. Some compounds showed evidence of processing by cosmic rays, creating products that do not naturally occur on planets. These radiation-altered chemicals acted as timestamps, providing clues about how long the object had wandered through the void before arriving in our neighborhood.
The ongoing analysis felt like a real-time lesson in comparative planetary science. As more telescopes joined the observation campaign, the chemical catalog grew more detailed and complex. When astronomers plotted the visitor's path through our solar system, they discovered something that looked almost choreographed. The mathematics of orbital mechanics rarely produce coincidences, yet this object was following a trajectory that seemed designed for maximum scientific impact. Its orbit would carry it past multiple planets at ideal distances for telescopic observation, while at the same time avoiding close encounters that could gravitationally deflect its path. Consider the precision required for such a passage. Our solar system stretches across billions of miles like a vast cosmic ocean, with planets scattered like islands. For an interstellar visitor to thread its way through these gravitational influences while maintaining an observable path requires an extraordinary geometric alignment. The probability of such perfect positioning occurring purely by chance seemed vanishingly small. The orbit offered another remarkable feature: optimal imaging geometry throughout the passage. As the object approached the Sun, it would remain visible to Earth-based telescopes for months, never slipping behind solar glare or disappearing into daylight. This natural scheduling allowed continuous observation during the most active and interesting phase of the visit. Even more intriguing was the timing of closest approach. The visitor would reach its nearest point to the Sun in autumn, allowing major observatories in both hemispheres to participate in coordinated observation campaigns.
Professional and amateur astronomers around the world would be able to take clear shots at this cosmic target during the best observing season. At a distance of 4.5 astronomical units from the Sun, something magical began to happen. At this range, roughly equivalent to the gap between the Sun and Jupiter, solar radiation finally accumulated enough energy to awaken ice that had been frozen for millions of years. The process was like watching a time-lapse of spring arriving across an entire world. Ancient materials began transitioning from solid to gas. This awakening process followed predictable patterns that astronomers have studied in countless comets. Sunlight does not just provide heat, it delivers energy in precise packets capable of breaking the molecular bonds that hold ice crystals together. When these bonds snap, water molecules escape into space, carrying dust particles with them like leaves caught in a cosmic breeze. But these were not ordinary ices responding to familiar starlight. These frozen materials had formed around a completely different star under conditions that existed when our own solar system was still a swirling disk of dust and gas. The awakening represented a meeting of matter from separate stellar neighborhoods, separated by distances so vast that light itself would take decades to cross between them.
The process began slowly, with only a few molecules per second escaping from the warmest regions of the nucleus. As solar heating intensified, the sublimation rate increased exponentially. What started as invisible puffs of gas soon turned into streams visible to powerful telescopes, and then into clouds large enough to envelop entire planets. Think of the nucleus as a dirty snowball the size of a city made of ice mixed with rocky debris and organic compounds. As the surface layers vaporized, they exposed fresh material beneath, creating a continuing cycle of sublimation and dust release. The object was literally evaporating before our eyes, losing thousands of tons of material every day.
The awakening also triggered the formation of the characteristic cometary tail. The solar wind, a stream of charged particles flowing outward from the Sun, began pushing gas and dust away from the nucleus. This created two distinct tails, one composed of ionized gas glowing blue in photographs, and another made of dust particles reflecting yellow sunlight. As October approached, our visitor was nearing the most dangerous moment of its billion-year journey. Perihelion, the point of closest passage to the Sun, represented both the peak of the comet's display and its potential destruction. At just 130 million miles from our star, the object would experience heating intense enough to vaporize rock and metal. For a traveler that had survived the icy darkness between the stars, this solar encounter would test every aspect of its structural integrity. When the Hubble Space Telescope turned its gaze toward our cosmic visitor, it captured something unprecedented in the records of interstellar astronomy. The image that emerged from Hubble's cameras surpassed every previous photograph of an interstellar object in both clarity and detail. Where ground-based telescopes showed only a fuzzy blot of light, Hubble revealed structures and features that transformed our understanding of what we were observing.
The resolution was so sharp that individual details became visible for the first time. At the center of the frame, a bright point of light marked the location of the solid nucleus, though the actual rocky core remained hidden within an envelope of gas and dust. Surrounding this central marker were streams of material flowing outward in patterns resembling frozen fireworks. Each filament told the story about the forces that had shaped this ancient traveler. The most striking feature was the overall teardrop shape. Unlike the spherical halos that surround many comets, this object displayed a distinctly asymmetric profile, pointing directly away from the Sun.
This shape revealed an ongoing battle between solar radiation pressure pushing material outward and the nucleus's weak gravity trying to hold everything together. Hubble's image also captured something never before seen in an interstellar visitor, clear evidence of active sublimation occurring in real time. Bright jets of material could be seen streaming from specific regions of the nucleus, creating fountain-like patterns that shifted position as the object rotated.
Perhaps most importantly, the Hubble image served as a historic document. It was the clearest image humanity had ever obtained of material from another star system, preserved in exquisite detail for future generations to study and appreciate. The reality was that we were not just looking at a comet, but at a messenger carrying samples of an alien world directly to our telescopes. During millions of years of interstellar travel, invisible cosmic bullets had slowly reshaped the surface of our visitor, one atom at a time. Cosmic radiation represents one of the most persistent and destructive forces in interstellar space. It consists of high-energy particles accelerated to nearly the speed of light by stellar explosions, black holes, and other violent cosmic events. For us, this discovery told the story of a traveler carrying samples from one of the oldest stellar environments in our galaxy. Our visitor came from the thick disk, a region containing metal-poor ancient stars that formed when the Milky Way was half its current age. Chemical archaeology revealed that the ice now sublimating under our sun's heat had condensed around a star that was shining when the galaxy was less than half as old as it is today. And now, this ancient traveler is passing through our solar system, delivering messages from the distant past to us. With each passing day, it reveals more of its secrets, telling us how it crossed that vast interstellar void, how it survived, and scientists are listening carefully. As researchers race to make the most of this unique opportunity, they continue their observations with the hope of discovering many more such visitors in the future. Because we now know that interstellar space is not an empty desert, but an active environment filled with cosmic highways connecting the star systems of our galaxy. And we are small observers of this great cosmic traffic. Thank you for listening. Don't forget to subscribe and like so we can be together for more observations. Good night.